Sorry. We tested and it flagged.
Flash like the previous one? It'd be great to find a solution to the flash.
All right, everyone. All right, everyone. We're going to go ahead and get started. We're right on time. Our next talk is by Michiel Stock, and he's going to be talking about a general-purpose toolbox for efficient Kronecker-based learning.
Okay. So good morning. Indeed, I'm Michiel Stock. I'm a postdoc from Ghent University. And in my research, I develop machine learning methods for pairwise learning. So methods for learning to predict interactions between humans, between molecules, species, and so on. And to this end, I use a lot of Kronecker products. And in my package Kronecker, I've aggregated a lot of tricks to make it easy to work with them. So firstly, for those who do not know what's a Kronecker product, well, a Kronecker product is just a specific type of product between two matrices of arbitrary size, suppose here A and B. And the Kronecker product is just a way of combining all the combinations of elements of these two matrices as shown here. So written explicitly, you see that this yields a very large matrix and with all the element-wise combinations. And computing this matrix, this is in the base of Julia, this can just be done with the function cron. My package is a computational improvement or alternative to that. So why should you be interested in Kronecker products? Well, because they appear everywhere in applied mathematics. So they are, for example, used in optimal control, Lyapunov equations. They're used in modeling networks, Kronecker graphs, and they're used in modeling they're used in modeling matrices using the matrix normal distribution. I also use it for pairwise learning, obviously. And the reason that these Kronecker products are so popular or that they are so easy to use is because there are a lot of algebraic tricks or shortcuts for working with them. For example, if you want to compute the inverse of a Kronecker product, that's just the Kronecker product of the inverse of these matrices. Same tricks are for trace, determinant, and so on. Of particular relevance to my methods, for example, is if you want to multiply a vector with a Kronecker product, and this vector here is represented as a matrix X, which I vectorized, so I flattened. You can rewrite that as just a reshaping of three matrix multiplications. And this is much more efficient because you can circumvent computing this very large Kronecker product matrix.
The mixed product is BD, no? BD, not BC? Otherwise, D doesn't show up.
That's a typo. It's correct in the package. Unit tests. So really the trick is if you use everything on the right hand side, you can do this much more efficiently, all these operations. And my package is just a way of working with that. So I defined a new abstract type, generalized Kronecker products, which is a subtype of the abstract matrices. And a concrete instantiation of that, so a struct, is nothing more, here this example is Kronecker product, there are other special cases, is just a container for the two matrices, which does not compute the Kronecker product directly because we want to circumvent this. And then the only thing that I've done is overload all these other functions so that they use these tricks on these matrices directly. And the API of my package is, I think, quite intuitive. So we can use the function Kronecker to compute this lazy Kronecker product or generate this lazy structure. Or if that's your thing, you can make it feel more mathematical by using Unicode, so the symbol for the Kronecker product. If you do collect, you can generate all this matrix explicitly. You should not do that in practice, but you can also get individual elements. Now, the basic functions of the linear algebra package, they are overloaded for these shortcuts. So either they yield a number, as in the example of trace, or if they yield another matrix, like this invert, they also yield a lazy data structure. So this is efficient. And then if you want to multiply with a vector, or if you want to solve a very large system of equation, this is done in standard Julia syntax, but this also uses the shortcut. And then something which was initially to me a surprise. So I first developed this for product of two matrices. And to my big surprise, this automatically worked as well with 3 or more matrices. And this is because the type system of Julia is so flexible and it perturbates all the mathematics, which of course makes sense. So this also works for higher order products. Let's take a look at the performance. So this is CPU time versus the size of your Kronecker product matrix. And these broken lines are the native functions in Julia, and these full lines are the different functions of my package. And you see that there is quite order of magnitude speed up, as would have been expected. So note that the main bottleneck in practice is actually not time complexity, but it's rather memory. At some point, these matrices become too large that you cannot store them anymore in your computer and totally breaks down. Now, up to now, you assume that the system is complete. So this is a bit typical of my example. So if you want to multiply a vector, so a flattened matrix with this Kronecker product between these two matrices, it can happen, especially if you work with data, that your matrix is not complete. So for example, if X is an image we want to model, we might not have the complete image, but we might have missing pixels, or we only have some pixels at some positions, and we want to try to impute this. So if this is incomplete, this data set, then you cannot use the standard vectoric, but there is a generalized vectoric which does work with that. And this is the generalized vectoric. I won't go over it into detail. This is for working with these incomplete Kronecker systems, and as you can see, it's quite for loopy, so it's easy that it's convenient that you can implement this quite performantly in Julia directly. And if your data is incomplete, then you can just use indexing to say, okay, I have this part of my matrix that I have sampled, which I want to work with. And this index Kronecker product is just the Kronecker product type plus all these indices. And if you multiply this with a vector of the correct size, then it will just use this generalized Kronecker product to be quite performant. And this was a brief overview of my package. I initially developed it for our in-house problems, so for developing machine learning methods, but I also hope that it can be of use of some other persons. Okay, thank you, and if you have any questions.
So just a reminder, if you just came in, questions should be asked here at the microphone, and I can't bring the microphone to you because so everyone can hear, and also so the people on YouTube watching can hear your question. So we have time for maybe one question. Okay, unfortunately, since it seems like we're having a lot of turnover right now, I think everyone can bring their questions to Michiel offline afterwards. So let's go ahead and thank him again.